5 for Physics 2211, where we are going to observe the motion of a slinky dropping. So in this lab, we see Newton's second law come into play, which says that the net force is equal to the mass times the acceleration. And within this lab, we will see a constant force. So our net force is equal to 0. And we have no acceleration because our weight force and our tension are equal and opposite. And we'll have a non-constant force where the net force is equal to the weight force and the drag force. So we observe a slinky falling, and we will extract our data and create a computational model to predict the motion of the slinky. So first in our code, we must input our initial conditions. So we want to put our mass, which is measured, our initial position, which we can extract from our tracker data, and our initial velocity, which we know is 0. Then we want to insert our gravitational constant, which we know as 9.8 meters per second squared, and indicate that this is going to be in the y direction, as well as our drag constant, which we extracted from our observed data. Next, we want to insert a while loop, and this will run through the time that the bottom slinky is motionless. So during this interval, our net force, as we said, is constant, so it's equal to the weight force plus the tension force, and we know that these are equal and opposite. We also want to update our velocity and our position of the ball, which we can derive from Newton's second law of motion. Then we want to insert a while loop where the bottom slinky is in motion. So this is to our final time. And here we have our non-constant force where our net force is equal to the weight force plus the drag force. And again, we want to update our position and velocity. So here we can see our observed model in the blue versus our predicted model in the orange. And these have relatively the same position versus time. There are some slight variations. This can be due to in Tracker when we grabbed our data. The video was not of the best quality, so it was hard to tell exactly where the bottom of the slinky was. As well, it spun a little bit. It didn't fall exactly straight. So we have some slight variations in our graphs. However, we can use these models to predict the motion of a falling slinky.